Okay, folks. So my slide is basically covering the two things that we're interested in here: gravitational waves and EM as signatures of black hole mergers and AGN disks. So on the top, I have some figures from a paper that myself and Salik are working on with Richard. Hopefully that'll be up on the archive in a couple of weeks. And, our goal is to sort of come up with this sort of zeroth order chi-effective distributions for mergers in the bulk of the AGN disk, so that we can compare the distribution that LIGO gets from O3 and O4 with what this channel predicts. So in this paper, we're kind of looking for qualitative differences in the chi-effective distribution because there's so many unknowns that you want to do things like change your disk model, change your assumption about, say, the existence of a migration trap or not, have efficient grind down or zero grind down, have a disk that lives a short time versus a long time, so that you can kind of see the gross features in the resulting chi-effective distribution. You can make assumptions about a flat spin prior, so uniform distribution from A is minus 0.98 to plus 0.98 and select randomly from that. Or you can assume that there's a narrow spin distribution, maybe from a previous long-lived AGN episode, or the black holes are born with narrow spin, for example. So the top is really kind of a guide as to where I think one of the directions that we need to go in the next couple of years, right? We need to make predictions for this channel that LIGO can directly give us feedback on. And this is obviously not going to be the final word, right? We saw yesterday that we don't have a good understanding yet of the torques that cause mergers. We don't also understand the eccentricity distribution of mergers in AGN disks, right? So I think we should view these as the first zeroth order chi-effective distributions for this channel that then become iterated as we learn more about how torques work, how feedback works, as we change our expectations, right? Does type 1 migration hold, because that's an assumption here, or do we have to moderate that, right? Are disk models closer to something like a Sirkin-Goodman model, or are they closer to something like a Thomson-Quadrant-Murray model, or something else, right? So these are the sorts of things that we want to zero in on over time. On the bottom, then, we have other ways of searching for these objects. So on the left-hand side, we can look for so over here, I'm plotting a prediction for Athena for the RNK alpha profile, the broad RNK alpha profile, for a binary system, an SMBH-IMBH binary, with a mass ratio of something like 1 to 100. So this would be a really large IMBH, close to an SMBH. And basically what you can do is you can use the same radial velocity trick that people use to find Jupiters, hot Jupiters around stars, right? So the innermost accretion disk is stapled to the SMBH, and the SMBH then wobbles around the center of mass of the binary, and so you get this. The central SMBH will kind of wobble and give you this Doppler shift from red to blue to red to blue over the orbital time of the secondary. The really cool thing about this, I think, is that We can, in principle, do this with XMM now, but only on a small handful of objects. And there's a natural calibrator for this wobble, which is the narrow RNK alpha line. And that's supposed to come from material that's much farther away. It's going to respond on much longer timescales integrated over a much larger volume. So we have tools that can be used to probe a very efficient mode of the AGN channel, right? So if we manage to build up sufficiently massive IMBHs in AGN disks. The other tool that we have is on the right-hand side over here. We want to think about how a memory disturbs the innermost AGN disk and the signature that will imprint on X-rays. So Aaron talked a little bit about this before. Sort of our idea back in the day was that essentially if you can excavate a little cavity as something falls in quite quickly, then you'll see a flicker in the broad wings of the iron line, because the iron line is coming from deep in the potential of the SMBH. It's essentially corresponding to the distribution of gas that's being irradiated by X-rays deep in the potential well. So if you disturb that with an emery, that could show up in the RNK alpha line. So, you know, if I'm being pessimistic about the RNK alpha, I would say that Athena is only going to observe about 30 of these broad RNK alpha lines with enough signal to noise that we can do this, right? 3-0. But if you want to apply the same trick to soft X-rays, you have a much larger effective area. So if you say that the soft X-ray excess, for example, is a series of blurred emission lines coming from the same general region, you can play the same game, right? You can look for some sort of periodic wobble. And in that way, Athena, you can use to get maybe 100 to 150 objects in the local universe that you can probe at fairly high significance. So that's what I wanted to say here. So hopefully that'll introduce some comments and thoughts.
Any comments or thoughts?
Yeah. I'm just curious about the number 30. I heard that actually 2 days ago it came up. What? How? Yeah, sorry, I'm waking up.
Yeah, I know. I haven't had enough coffee either. I got the...
Really a lower limit, or how is it calculated? I'm just curious.
I dug that up from the XMM project website.
That to me sounds great, actually.
Yeah, I think they can do about 30 now. And
Right, yeah.
so XMM probably has done these kinds of spin broad iron line measurements in about 30 sources. And Athena will have like 4 times, maybe 3.5 times the effective area at iron K. So it's not actually a huge improvement at 6 keV where the iron line is, but at soft energies, it's going to be like a 10-fold improvement or more. So there's that. That'll help. But also the sensitivity of Athena is going to be a lot better. You can hopefully look at more redshifted further quasars, and then the iron line is going to peak in the part of the energy band where Athena's effective area also peaks. So that may help you.
Do you have any other missions that you might suggest should fly that could maybe do some of this stuff? I mean,
well, so one probe mission concept is StrobeX, and that's going to have like 30 times the effective area of the soft X-rays of XMM compared to XMM, but it will have like 100 times the effective area of NuStar for hard X-rays. So it's really it should be able to do these iron line measurements for 100 AGN. Yeah, so that's going to be helpful.
I like the sound of that.
Yeah, so it's an easy question to vary. So considering all the backgrounds, all the practical difficulties, which hat would you wear to describe whether it will be done in the next 10 years?
Zoltan had a good point. He was going to bring his bike helmet. So maybe I'd wear that instead. I'm not sure which one
Safety
to
first,
wear.
safety first.
I genuinely don't know. I think we should exploit these tools that we have as much as we can and see what we get, right? Even if we only manage to get 30, that's still going to give us a reasonable constraint on the priors that we want to put into our models, right? So.
And also, like the Iron K line is, I really like this work because it is such a clear signature and it's a really nice prediction. But it's not. It's also, it takes a lot of photons to get an Iron K line, broadened Iron K line, and modeling it and stuff. So, you know, maybe what we really need to be thinking about is other observables where you can just use photometry to, you know, just looking at a light curve, like what are the predictions that you expect,
Right.
and that we can do with, you know, many thousands of sources.
Right. Yeah. Sorry.
Another idea is if you have a star transiting in front of or eclipsing the source, in principle you have a chance to see if there's a gap or not in the disk or a cavity.
Right. So.
No.
Yeah. So Bensei's talking about the notion that you could have an eclipse of an AGN, right? If there's something in the spherical volume that sort of moves across the face, then particularly in the X-ray, maybe in the UV, it's going to be easier to see a sort of sudden rapid change. And we have seen a few, maybe on the order of 10 such eclipses of the central X-ray emitting region of AGN, and that allows us maybe in principle to map those central regions. So if there are obvious distortions of the central disk, then I think this is a good way to map that. It's the only way, in fact, of mapping the X-ray region, the spatial distribution, right?
That won't work. You have to actually download them. You're just downloading the key images.
Oh.
But yeah, just back to
Actually, yeah.
I'll keep talking. Back to what Aaron says, I think maybe the way that we want to think about X-rays anyway is to look over these large numbers of objects and see if we see variability clues, and then maybe zero in on the Iron K alpha and see if we can catch something, right? So a TOO, right?
Like,
Sorry, I'm learning to drop out.
No worries.
I'm also trying to upload to the Dropbox now.
Yep, cool.
Yeah, I think what Chelsea's finding and what a lot of these time domain surveys are finding now is that there's kind of extreme AGN variability that we never expected, and there are such clear predictions for tidal disruption events, so everything becomes a TDE. And I'll show you one that actually later today that I can't explain its crazy AGN variability, and so I like the TDE, idea. But if there were such, I think that it's even possible that we've already seen some kinds of signatures that we just don't know what to expect right now, and we're calling them all TDEs.
Right. Yes, one point that I'm going to call out later in the sort of what do we want over the next 2-3 years is phenomenological modeling in EM for AGN disks. So in changing state quasars that hopefully Chelsea will tell us something about, we want to be able to explain these crazy changes in the quasars that we're observing, and we want to get a sense of whether these are unusual or maybe not so unusual, right? Because that's going to give us a clue as to what the population of these disks actually consists of.
All right, as I've been looking quickly through the barrage of new Dropbox files, a really good one to follow up with that might be this one.
You can hear that.
How do I make it bigger? I'll just do this.
Yeah.
No.
And so here's a crazy change. The bottom two left panels. This was the most dramatic change that I found with this spectroscopic campaign of like 130 or so, 100 or so of these candidates. Anyway, so this one was selected by light curve. You can see in the left bottom, and the blue points that kind of have like a big gap, going from the beginning Sloan points to the later Pan-STARRS data, are the G band, and then just above those are the purple points, which are the R band, and then the red is the CRTS light curve, which is open filter, so it's brighter than all the other bands. And you can see it just kind of drops off a cliff at the end there. So we got a spectroscopic we got a follow-up spectrum in the right-hand panel shown in the blue, and it's much dimmer as you expect. So the blue continuum went down, and the H beta line is now absent. So yeah, this was the most dramatic one we found. And just, I guess, looking back at the light curve to comment on what y'all were saying earlier. So I mean, this is kind of a rare type of variability. And I think that, the light curves of these very crazy variable sources are all very diverse. Now, the ones that are flickering kind of on and off, instead of just dropping off a cliff once, those will be flickering back between these two states, so you'll see less of a dramatic effect. Like the effect that you see won't be as dramatic, because things are constantly getting heated up, and so my other concern is, I mean, we haven't understood quasar variability for like 50 years. So, yep. And now we're finding these exciting large changes, but really just because we have a longer baseline to compare observations with. I mean, are we going to learn much more by studying the light curves? I feel like it's going to take a while just to collect the data because they're slowly varying. Maybe we should just wait for more gravitational wave events. I don't know.
I need that man's hat.
I know. Yeah, I need the Yankees hat right now.
So I think these are really awesome. I think they're really fascinating insight into quasar disks. So I definitely enjoy seeing these, sudden collapses in the blue. You're totally messing up the inner disk here, whatever's going on. So it's an interesting, whatever it is, it's really cool, literally. But so, the thing that sort of occurs to me is that these changing look or changing state quasars are maybe 1 in 10,000 quasars, something like that. And so it would be really interesting to tie that into the expected Emery rate for n objects embedded in a disk of a particular density profile. How many things do we expect will fall onto the main object, on average in an AGN per year, right? Someone needs to write that. Can someone please write that? Okay, I mean, I can do it, but, so yeah, that's the sort of thing I think that will help constrain our models of the disks and the populations within them, right? If we come up with too high an Emery rate, then that can't be the explanation for this. And we have to downgrade our density profiles or assume fewer n embedded in a typical quasar disk.
So on the COQ fraction,
Yeah.
I have a really hard time answering that question, what's the rate? Was it 1 in every 10,000 objects or what, or 1 in every 10 objects? Because I find it continuous distribution, right? So they're the tail.
Yeah.
And so if you define them as being this variable, yeah, it's going to be pretty rare. But if you define it, more moderate, just enough to like where H beta disappears, then the rate is much higher actually among. So that I quote the rate up there, but that's just among the highly variable quasars at the same redshift.
Right.
So I just have a couple. So your question is how quickly, I can't quite read, does the light curve change on the lower left panel? Is that months, years? Like how quickly does it change?
Like the red going down is
Yeah.
probably a couple years. Yeah.
Oh, sorry.
A couple years.
Yeah. Okay. And do any of them change back their look?
Yes.
They go back. Okay. And then the last question is that feature on the right, did it go away in the spectrum, or is it just not out of range of that blue?
Of the H alpha
Yeah.
aspect. You're talking about H alpha on the very right. It's probably still there in the narrow and most likely a slight amount of broad. But there are quasars that change look like this it does change all the way to a type 2. You don't have any broad H alpha either, but that's way more rare than this. Oh, yeah. Thank you.
Yeah, I see periodicity everywhere. Before the big drop on the red, it looks to me very periodic. Is that been checked, and is that typical, or how these, or is it just some random thing?
Oh, so
Is
it's
it
kind of looks like a saw blade, kind of like. Is that what you're talking about?
Yeah, I see repeating pattern of up and down before the drop.
I'd say it happens often. Yeah. Yeah, I haven't looked at the detail into detail on that, but yeah, I'd say it happens in some other ones. Actually,
Yeah, I think you showed me.
I showed Dan one time too. And yeah, it looks kind of like a saw blade like this.
Yeah.
Right. And not sinusoidal. That's.
No, not sinusoidal.
As of today.
Oh, thanks. I thought you were going to stop halfway. Right, and I was just responding to Andrew saying they don't, if there's some periodicity, it doesn't have to necessarily be sinusoidal. Zoltan and I have been looking at eccentric binaries causing sawtooth-shaped modulations in waveforms.
So, I was just going to say it's CRTS data, and I've spent enough time with Matthew Graham to know that don't read too much into bunches of points necessarily on very short timescales. Just you could fit a straight line across there. Don't.
I'm not sure you can. I mean, the error bars are probably.
The error bars are big.
The error bars are probably much smaller than the excursions, but I think it could be just.
I'm showing medians. Yeah, I'm not showing the error
Anyway,
bars
it could
there.
be assessed, I guess, quantitatively, whether that's significant or not.
Yeah, it could be. Good point.
I think the next most relevant one, to continue our discussion of optical variability, is Vermeerjan's.
I'll take that one.
Yeah.
I'll bring you this microphone.
There you go.
All right.
So yeah, it's funny because we're somehow reproducing RV measurements, and now I'm talking about transit equivalence, although we mentioned that a little bit before. So my approach is, again, to be specific, this is not something that we're going to be catching when the things spiral into each other. That moment is just too short. This is talking about whatever is disturbing the disk, those black holes, either as they're coalescing, as they're getting trapped, as they're getting whatever disturbance they're doing. This is the kind of thing that I think we can catch. But first and foremost, fundamentally, AGN are bright. Quasars are very bright, or very luminous, certainly. But what you want to do is err on the lower luminosity side, so that gives you contrast. But the most contrast you're going to get, because your disks are still putting out an enormous number of photons in the optical and the infrared, you want to go where whatever is happening on the smaller black hole side has a chance of competing with the overall accretion disk from the supermassive black hole. So that really pushes you to the UV, to the far UV in the X-rays. So I think that's the first step, that any kind of observational predictions that you're doing, ideally, what's the consequence at those wavelengths, because that's where we have the best chance of picking things up. The other one is that, in general, an instantaneous measurement has a lower chance of giving you something of the types of things that we're looking for, like Chelsea was just showing. Variability is, in some ways, easier to identify because you're doing a difference. So there's the delta measurement, and so the delta measurements are oftentimes easier. And the reason I put a transit curve up here, it's not just any transit curve. This was by the MOST satellite. If most people don't know about MOST, but it was a small satellite launched by Canada. It's about the size of a briefcase. It has a 15-centimeter telescope. It was for asteroseismology, but then they went and started doing transits. With a 15-centimeter telescope, they were able to pick up a very nice transit. Why? Because it was a dedicated mission. So I think the likelihood of us trying to pick things up is going to be less if we're trying to ride along with other missions, but smaller but dedicated missions will have a better chance of picking things up like this. Is that easy to do? No, space missions are hard to get. I'm trying to push for cheaper, smaller missions, which are less costly, so we can have more of those. But the reality is that they are very hard to get. But think about this. Within the past, now 15 years, NASA has approved 2 X-ray polarimetry missions. Nothing wrong with X-ray polarimetry, but it's fundamentally, that's not a large portion of the population of astronomers who do X-ray polarimetry. But the science was exciting. It got NASA to do it because that was very interesting science. Unfortunately, one of the missions went over budget, but then another one was approved again because it was exciting science. And I think this has the chance of being very exciting science. Obviously, we're here, so we're biased, but I think to think about it is not, I'm not saying it's a high likelihood, but I'm saying that there's a better chance when your science is exciting to get something, even if your population amongst the astronomers is not. So it's not always servicing the large population. And in this case, we can, with a dedicated mission, they were able to pick up something like this. And of course, Kepler is a better example later. It's a much larger mission, but we have a whole slew of range of missions that we have the potential to apply for. And then, of course, there's the timescale variability, which is the numbers that are something that, if you have a dedicated mission, what's the likelihood that you can pick it up? And then there's this trade-off between the number of photons you're getting and the timescale variability. If the number of photons you collect, the amount of time you need to sit and collect them is longer than that variability timescale, then you're going to wash it out, forget about it. But then that still defines, at least in the UV sense, your mirror diameter, about how many photons you collect. In the X-ray sense, your collecting area. So fundamentally, that's a number that is very necessary to even first think about what kind of a mission this can be done. But of course, when we're talking about UV and X-rays, it's only space. It's not likely we'll be doing this from the ground. And then finally, sample size. How many do you need to look at? This is the kind that Barry was just talking about. But it also links between all of the kinds of things that we were just talking about, is how we have some sense of how AGNs vary in these sort of large scale, dropping down to blue, or various other things, but at the end of the day, we can only look at so many. So we need a reasonable estimate of, okay, this is 1 in 10, 1 in 100 or something, so that sets up the final sample size. And ideally, then, what you want to do that has to be an intersection between whatever your sample size is with the kind of AGN you're looking at. Nearby Seyfarts are very bright. Low luminosity AGN are exactly that low luminosity, but they're still nearby and bright-ish. You have a sort of high luminosity quasars that are still bright, but as you go higher and higher redshift, the time scales change. But how we sort of subsample the AGN that we can observe, the sample size is going to be a driver for any of this. So I think these are the kinds of things that, as you go forward in modeling, these are the kinds of numbers that anybody who's going to be involved in designing a mission, like myself, or proposing a mission with a science team, really, these are the kinds of numbers that we have to have. But the one thing I really do want everybody to know that don't think about this as niche science in the sense that, well, it's a smaller community that's doing it. I think fundamentally, gravitational waves obviously are one of the most exciting things to come along, and I think exciting science can get dedicated missions.
Where's the microphone?
Oh, sorry. You're out.
I got it.
So I absolutely agree with what you said. The thing that sort of occurs to me is I think we can come up, there are a lot of bright people here. We'll come up with signatures that we can test in the UV. But the thing that we would need a small scope to be able to do is rather than sit on one object and pray that something's going to happen in it, right? You want a very rapid slew to, oh, hey, something's going on over here. Let's sit on that thing, right?
Yes.
So I think that's ultimately where we would end up.
That's definitely that's an option. That sort of goes to the sample size argument in that sort of the, do you want to just do, let's look at a whole bunch of things and hope that something, we'll catch statistically one of the things that's happening, or we have a trigger at which point then we become much more of a TOO kind of observatory. But that's eminently doable. There's nothing that prevents you from doing that. And I have to also say, we are getting woefully, late in the mission lifetimes of the two main UV observatories that we have, Hubble and Swift. So there's going to be another UV observatory coming soon. A generalized UV observatory, again, this will be much tougher to do, but I think people will be sort of turning their attention back to UV, which was sort of the driving force for space telescopes for the longest time, and then sort of hasn't waned in interest, but now it's coming back up. So I think there's definitely that approach, which I think is a perfectly fine approach, particularly because, again, how are what's causing it? Is this some sort of a shock or something that has other consequences, which may be ambiguous or degenerate with other things, but certainly is worth for us to go and look at those. So that's a powerful additional way of thinking about it is what other consequences are there at other wavelengths, even if it's not unique, but it will have a unique signature in the UV so that it allows us to follow up in a way which we wouldn't otherwise do. I mean, every variable, all AGNR variable, that was the definition of them from the beginning, or at least the seed that gave us the accretion disk model. So, but I think this is doing follow-up is a really powerful technique of getting what's going on.
So just following up on the follow-up idea, I think I agree. I think that it's got to be a two-pronged approach, right? Of course, like we have to understand what an AGN disk looks like, even without a black hole embedded in it, to be able to compare to these large samples. And then I think that probably I agree that follow-up fast slew is going to be how we nail this down in a particular object. But then my question is, like, how long should we expect any signature to be? How fast do we have to slew? And how long do we have to monitor it? So that's kind of like the question that I would want to know.
Yes.
So yeah, that definitely goes under sort of the time scale argument here. That is, if it's something that lasts an hour, it's not likely going to be something that we can just collect enough photons, before that hour, during that hour, multiple times, and then afterward. But if it's something that gets on the order of days, I think that becomes very much within the realm of the possibility, and weeks is way, that's definitely perfectly within the technological aspects of what we can do right now.
So certainly with the CSQs, we see this cratering in the blue over, I guess, Chelsea, weeks, maybe even less, right? This is like the collapse. If we catch it, it can be very fast.
Like on a month, yeah.
On month timescales. Okay, so that should be we can easily do that for slewing.
Also, in particular, I think I'm really very interested in seeing the newer time domain surveys, particularly what they have to say the difference between Seyferts and quasars about what the collapse is like. It may be smaller, but then, they're again nearer and brighter, and it's easier for us to pick up the photons to follow up on those kinds of things. That's, I think that's the realm that to always think about is fundamentally how many photons are we getting from any of these systems, both from the actual smaller black holes in the accretion disk, but also to some extent think about, again, in the transit analogy, it's harder to look at faint stars for the transit just because it's hard to get a signal to noise from which you can see the 10th% dip or 100th% or 1,000th%. So we need bright sources so that when we do see a change, even if it's at 1/1000th%, you have a high signal to noise, so then you can pick up whatever the change is.
All right, awesome, thanks. Keeping with our theme of photons, it's not in here yet. Okay, all of you who are adding things to the Dropbox, you can stop now. Because I'm behind. All right, see how it's growing. Okay, I'm just gonna download everything for the millionth time. All right, AM Wednesday. Wait, did I get the wrong one?
Yeah.
2, oh, for goodness sakes. All right, Aaron. Hand the microphone, thanks. There are 2 slides. I don't know if that's allowed. Let me know if you want me to.
I'll give her a bye.
All right.
Speak twice as fast.
Well, I only have to do one.
2 first names, so you get 2.
That's right. Okay, so I wanted to start out with some questions for you guys on how we're actually gonna find these things. And we've talked a lot about some of these things already, so this can be quick. A lot of what we've been discussing, obviously these things are orbiting, and so it's like easy to think of, oh, there would be like some kind of periodicity, some kind of QPO signature, and that's the observable that we should be looking for. But the thing is, we see QPOs and periodicities all the time, and it's really hard. Well, first, and in addition to periodicities, AGN vary just red noise. So Zoltan can tell you how hard it is to compare, to definitively say that something is a QPO or a periodicity versus just red noise. So, yeah.
Just to be clear, if this mechanism actually works, pretty much any quasar with a decent nuclear star cluster should be suffering from black holes in its disk, right? So this isn't necessarily a damaging statement. On the other hand, I don't think we can see all of these because they're buried deep in the disk until you get up to gap clearing.
I'm not saying that signature doesn't exist or we shouldn't also look for it, but I think that in terms of making predictions, if you can do something beyond expecting a periodicity, I think that's like the smoking gun. If you want people to believe that any of this is actually happening, it's got to be more than just a periodicity. That's the point. So like Barry's work on like shifting iron lines or shifting, H alpha, well, I don't know, but some kind of, something, that spectral feature that changes with phase, for instance, would be interesting. And then, yeah, so I'm also thinking about like, should we be targeting specific galaxies, specific AGN types? And I know that these are all open questions and, but just things that I've been thinking about this week. Should we expect these more in ADAFs? Should we look for low luminosity, target more low luminosity AGN because those are the systems where maybe we'd have a hope of seeing some signature from a stellar mass black hole in it, or maybe we should be targeting maybe we have a better hope of seeing this in a very efficient accretion flow, a thin disk where some kind of migration trap occurs and or maybe like evacuates the inner disk, and we see that very obviously in a light curve, for instance, and changes in a spectrum. I'm not really sure. And then and then like in tidal disruption events, one of the things that's been kind of cool recently is that they seem to appear mostly in these rare E+A post-starburst galaxies. And, that was an observational kind of thing that came out of just, looking at several of these. But maybe it makes sense that you expect more stars entering the loss cone in these kinds of post-merger systems. And so is there some kind of thing that some kind of galaxy where we might expect, some kind of AGN where we might expect these stellar mass black holes to manifest themselves in the AGN, like more in those kinds of systems. And then, one of the other things is that I'm interested in is what waveband should we be looking in? So we talked a lot, or you guys talked a lot yesterday about where these black holes are actually going to merge. So when there is a LIGO event, is it going to be happening at very large radii? And then maybe it's a little trickier because you might expect that the disk is emitting in the optical there, and you have, other contaminating effects, or is it going to happen in the innermost regions? Should we be looking at the UV? If it's in the innermost regions, we could perhaps see a crash in the X-ray emission. Like these are the kinds of, and is there an idea about like, okay, now we see like 260 solar mass black holes merging, and so that is more likely to be associated with the inner part of the disk, or can we kind of tailor our predictions for what kinds of electromagnetic follow-up would be appropriate based on like the LIGO events. And then I just wanted to show the kind of thing that we're thinking about. I'm on one of these, I'm like on a couple of these probe mission concept studies for the decadal, and AXIS is one of the ones that I've been working on. It's basically super Chandra. It's like 10 times the effective area of Chandra and twice the spatial resolution across the entire 25 by 25 arc minute field of view. So, and it has fast slew. So it's sort of like slew, it's like Swift with 100 times the effective area. And so it's going to be great for things like EM counterparts to supermassive black hole binaries. And the reason we kind of, if you can just ignore this horrible font that we selected, it kind of goes through a potential down selection. So like LISA, there are thoughts, there's lots of uncertainties onto the rates of LISA sources and the kind of the error boxes that you should expect, but they say that there should be one per year with an error circle of 1 square degree. And that's something that's totally manageable with an instrument like AXIS. So in that one, this is just an example so you kind of get the idea of some of the things that we're thinking about for finding electromagnetic counterparts, and maybe it'll trigger some ideas related to these kinds, this channel. So in a 1 square degree, LSST is going to see 60,000 sources. Around 1% of those will be AGN. And so by tiling that in X-rays, then you have a very clear indicator of which of those 60,000 sources is an AGN. So that gets you down to 600 sources. And then, maybe you prioritize galaxies that are disturbed, and LSST will be able to tell you the morphology of those things. And so that gets you 1 in 10 galaxies are disturbed. That gets you down to 60 sources. You get a redshift, photometric redshift from LSST, And you can compare that to the distance measure that you get with Lisa to within 10%, so you can kind of narrow that down to 6 sources. And then the other thing is that dual AGN preferentially are found in obscured systems. So you might not even be able to see these things in the optical, and you may only really be able to see them in the X-rays. And so you could, if you get spectra, you can also see favor sources that have some kind of obscuration. And then that gets you down to a magical number of 2 sources. So that's kind of like where I've been thinking, and maybe it's helpful for thinking about this work as well. Yeah, so I can.
Sorry, what was the X-ray instrument?
This is Axis.
Axis. Okay.
Yeah.
So sorry, just clarification. You're talking about supermassive binaries here, or
Yeah,
stellar
that
mass
was
binaries?
Right. This was just for supermassive black hole binaries.
And what is the field of view axis?
It's 26 by 26 arc minutes.
Because can't you then do possibly doing it before the merger? Look at the source even as the merger is unfolding.
Yeah, exactly. So that would be the hope, is that you'd have warning time, which I read from your paper is like two weeks, and then you can look for things like weird SED or periodicities in the sources that you narrow down. Yeah. But for like the case of these LIGO sources, stellar mass black holes, it seems unlikely, or maybe that's pessimistic, but okay, it seems unlikely that that we're going to be able to slew so quickly to see the actual merger, and then like seeing the electromagnetic counterpart, if it's embedded in this bright AGN disk, is also going to be challenging. But is there an appreciable effect on the disk on long time scales over several weeks? Yeah, yeah.
So I mean, there are all sorts of interesting effects, right, that might happen if you have n bodies embedded in these disks. And so you might expect, if there's some gas that loses angular momentum, suddenly you might expect a delayed, oh, here we go. Who's presenting that? Andrew, yeah, you should talk about this. Yeah, so you might expect a pulse of low angular momentum gas ending up in the SMBH post the merger, even though it's buried by the disk.
Yeah.
Yeah, so this is work with Zoltan and also Yeki Tang. And so it's a follow-up of what I showed on Monday morning, which was a binary, supermassive, but it doesn't really matter, binary black hole embedded in gas that is merging due to gravitational wave radiation. And on the left, on the top panels, the strain of early in spiral, and the bottom 2 panels are X-ray emission in a soft band in the middle and a harder band at the bottom. And what you see is a modulation on the binary period, but also on a longer period of about 5 times longer due to a gas lump in the accretion disk that delivers mass back onto the binary. And at early times, the kind of soft X-ray band is kind of a clean signal, and the hard X-ray band is a little bit noisier. But now if you look to the right panel, which is late in spiral and then merger, as I showed in the movie, there's gas all the way down until merger, and so there's still accretion and X-ray luminosity. But what you start to see is that both X-ray bands start to pulse together and in sync with the gravitational wave emission. So this is a potential signature of when something's about to merge, and then what you'd see at merger. Zoltan can comment too if he wants.
I think.
What is the mass ratio here?
The mass ratio here is 1.
I don't. I'm just wondering, again, more strongly, whether Axis could actually try to find this.
Well, so I wrote a white paper that's on the archive today about this, about X-ray follow-up of these kinds of sources. The thing that I struggled with, and I think that everybody is struggling with, is like, what kind of sensitivity do we need?
Yeah.
And like, what's the bolometric luminosity going to be? So we just assumed if it's like a typical AGN luminosity where you're at maybe 10%, Eddington, 10% is coming out in X-rays, we should still be able to see these guys out to a redshift of 2. So that's very good, but other, do we, like, that's, I feel like, kind of a pessimistic or conservative approximation, and I think we could get a lot more.
Yeah, so it's actually probably worthwhile to try to work this out in a little more detail. This is fairly crude radiation, so it should be done better. But one thing we discovered is that there can actually be extraction of the orbital energy of the binary that's going into shock to gas that can actually make these things potentially even brighter.
Yeah.
So I think probably a more detailed treatment. These are kind of scale 3. We can scale them to the different accretion rates. So using 10% Eddington is a good thing. So, but it could be potentially even brighter, or it could be fainter if we don't have the right opacity effects in the radiation.
Right.
So, but I think that was a good. So yeah, I'd be interested to read what you wrote.
Yeah. Well, Jeff helped me with it.
Oh, good. Excellent.
The answer I heard was yes.
Yeah, sounds you guess.
You can.
Yeah.
Redshift 2 is enough. I mean,
Right.
there should
For,
be.
for 2, 10 to the 6, so on.
But you have to tile the error box.
Yeah.
By, I don't know, 5 or 10 observations.
Yeah.
You're okay.
Please repeat
Yeah.
that.
I thought the main issue was you have to spend significant resource because you have to tile a few square degree box by maybe order 10 pointings, and you have to repeat it dozens of times.
Well, so it would take probably half of a day on each of those, or maybe less. So in, a couple days, you could tile the error, like, depending on, if you use those conservative estimates that we used, I think within like 3 days, you could probably get down to 2 candidate sources, or a handful of candidate sources, and then you follow those up. Do it many times and look for periodicities or whatever.
One just quick comment is that if there is variability observed, it may be that longer frequency. This is something Dan, who just left, pointed out. But so in fact, oh, Dan, you just come back.
Just keep sneezing. I need to get it.
Oh, okay. Well, I'll give you a warm up. If that variability is the longer frequency, then and then you infer how close the black holes are, it could be the case that they're already emitting gravitational waves significantly, because the true frequency would be the higher binary frequency, not the observed modulated frequency.
But actually, that was going to be my question: is which of those sort of corresponds to what's the higher frequency thing and what's the lower frequency one?
So the higher frequency is the binary frequency, and the lower frequency is, if you remember from Monday, the gas in the disk forms a non-axisymmetric feature.
Oh, I see. So one is sort of
delivers.
fluid, the other one is gravity wave induced.
Yeah.
Okay.
Yeah.
But it's still coming from the mini disk, right?
Yes, coming from shocks in the mini disk, and also gas impacting the disks that are coming in, and also gas being flung into the cavity wall at lower frequencies. Yeah.
It's not
So-
gravitational wave which induces this.
No, it's not the gravitational wave. It's gas. Oh, sorry. I didn't mean to say it was the gravitational wave. It's the gas that's interacting with the binary. So that, yeah.
But this is not the gas responding to any kind of gravitational wave
No.
emission. Okay. So okay.
So
That's a negligible effect. Sorry.
So I think this is, a good point to make the point that we want to be careful about what we think the gas is doing sort of this close in. And so, taking those careful numerical steps to make sure that we're actually going to get, right, in real life what we're seeing from these
Yeah.
simulations is important.
Yes,
right?
to do more careful radiation transport is a
Right,
key
right.
thing. And that's true of almost all things in astronomy.
But in this case in particular,
But I think this is much more robust than the torques, because
Yeah.
this doesn't rely on the really tiny thing around the sink. It's just
but this
gas.
does, no, hold on a moment. This does rely on being able to see it. And while that while a supermassive black hole binary might actually be able to be seen directly and therefore give these curves, the
What do you mean a binary can be seen directly?
so a supermassive black hole binary can clear a gap in the disk, in the optically thick disk, whereas the
But I mean, if it's emitting gravitational waves, it's at a milliparsec level. You can't see that.
you can see the emission from it though, whereas a stellar mass or superstellar mass black hole, or even up to intermediate mass, low intermediate mass, is going to be buried in an optically thick disk, and so these bottom two plots are going to be modulated by having to penetrate through to the photosphere of the disk rather than being clearly visible and being able to see every shock wave. And that's going to, I worry, get rid of most of the electromagnetic signal.
That could be the case for a stellar mass binary embedded in the center of a thick disk, that's true. And then the radiation transport would have to be done. It might blow it out. Oh, sorry. This is a lot of radiation. It could potentially blow out the gas and then start to radiate more efficiently. That's something that we should look at.
Apologies if this comment has been made this morning, and sorry for being late, but I just want to reiterate the fact that if you have a baby supermassive black hole binary, 10 to the 5, 10 to the 6 solar masses, you'll only see it in the LISA band for maybe a week or a few months, and that's how much time you have to follow it up, right? That's assuming that LISA eventually will beam back the information with enough time for you to follow it up with a telescope, and that not even that kind of beaming of the data has been established, like when the data dumps will happen. So, and if we want to think about the really big supermassive black hole binaries, I never on a normal day would make that catch, so I don't know. Maybe I should wear both of the hats. Yeah, feel better. And actually this does follow in the sense that if you have 10 to the 8 or 10 to the 9 supermassive black hole, I don't know. Today is my lucky day. I don't know if this is gonna get like 150 likes and 30 retweets like our video yesterday. I mean, I think that's viral for gravitational waves. To get to my optimistic point, if you have a 10 to the 8 or 10 to the 9 supermassive black hole binary, those are in the gravitational wave band for millions of years. And so that makes me very optimistic that we'll eventually find the host galaxy. But we should just keep these things in mind, right? That if they're emitting gravitational waves, you cannot point a telescope and actually see the binary because they're separated, by, in the LISA case, a few hundred gravitational radii, and then in the pulsar timing array case by milliparsecs. So you'll never directly image them, unless, of course, you have some sort of lens AGN. This is my super optimistic case now. If you have, and I think that we might talk about this, here we go Twitter. If you have a lensed AGN with a binary in it, then you can see the binaries moving in the lensed images, right? A back of the envelope calculation shows you can do this. But anyhow, my 2 cents. Thanks for your attention.
Did you want to say something?
Well, I think Mordecai, going back to Mordecai's criticism, I think it's fair. I just wanted to make the point it's less, the simulation result that there's a propeller which is throwing gas around on the orbital timescale. I think it's pretty robust. And one thing that hasn't been mentioned is that double binary stars, I mean, you just see these cavities, and you even see streams in ALMA observations. So there's empirical evidence that this basic crude hydrodynamics is okay.
Okay, well, wait a minute. You're still working in the center of disk frame. Now we have the shear that's trying to disrupt that cavity, and that's the calculation that I'm hoping Andrew will be able to do someday.
We can do it.
Wonderful, wonderful.
But I just So I want to make the point, just a slightly optimistic side, is that I think there's a lot of energy in the binary orbit itself, and there'll be outflows, and there'll be shocks, there'll be heated gas, and there'll also be a lot of radiation. So it's possible there'll be some interesting kind of fountain-like effects where the disk can be actually blown through.
Yeah, I agree. One of the big questions that sort of I hope that people are going to take away from this meeting is we need to understand what the effect of embedding these things in a gas disk is going to do to the gas disk, right? That's a key observational constraint on all of this.
Yes.
Yeah.
And just so everyone's aware, technically these things are becoming possible, but are still challenging to do the full radiation MHD. Yeah.
Can I have a
Oh,
mic?
sure, yeah.
All right. If there's anyone else who needs to leave after coffee, by the way, you should tell me to make sure we discuss your slide at the appropriate time. One of those people is Zoltan.
Anybody else has to leave after coffee?
Is there anyone else who has to leave after coffee? All right. Okay. Would you someone pass Zoltan a microphone?
Yeah.
Oh, that's happening. Okay.
Well, since we are dialing the photons, maybe we can go back to pure gravitation wave.
Yeah. So that slide was a good transition from the photons into the gravitational wave, since
So
it did
this
have
is a
both.
simple idea, which we had in that paper 2017. And going back to the stellar mass binary, which is inside the AGN disk, the idea is really simple, that this binary is orbiting the supermassive black hole in the middle. So if you look at the bottom left, this is the famous plot from Cesana's paper, where you see the object moving from the LISA band into the LIGO band. And so when the object is in the LISA band, this is a stellar mass. These are various masses for a stellar mass binary. I think this black one here is the first LIGO detection.
Yeah.
So it takes 10 years to chirp away from the LISA band and into the LIGO band. So when it's over here, it's a very wide binary, and it's living there for years, and it's moving around the nucleus. Now, it won't go on a circle all the way around the nucleus, but it's accelerating. So the orbital time around the nucleus over here, if it's at a good fraction of a parsec from a nucleus, it's 10,000 years. So in a few years, it's not moving much, but it's accelerating. So this parameter epsilon is just the acceleration v squared over r. So if you take an object 10 parsec from the nucleus, going at 100 kilometers per second, this number is 1,000. Just a normalization of the acceleration. And then you can calculate that due to this acceleration by how much the redshift of the object changes. So it's as if virtually all calculations of waveforms assume that the object follows the Hubble flow. It's just sitting in the universe. But this one is actually moving and changing its redshift, which imprints on the waveform an extra frequency-dependent term, which has a power of 13/3 or something like that. So it's not degenerate with other post-Newtonian corrections to the waveform. And then the question is, can you detect this? And there's actually at least three people. So one was Benza was involved, so maybe he'll also mention this. The observability, you just calculate a signal to noise ratio, where you take the change to the waveform and you divide by the noise, and you ask, is this detectable? And you find that yes, the signal to noise for detecting this is about 20 for this kind of acceleration for a 30 solar mass chirp mass binary. And then I had actually a double-sided slide.
Oh.
This is the back of my slide. Just to show you what is detectable. So this is the measurement error on this epsilon. And so these are marginalized over the other parameters. The bottom line is that if the total chirp mass is high, and you end the very important other parameter is when you turn on LISA, where is this object sitting? It's ideally sitting at the bottom of the sensitivity curve of LISA. So if it's sitting at this 10⁻² hertz, then you can measure this acceleration parameter. This one here, 3 × 10⁴, is roughly what we were talking about a couple of days ago. You have a 10⁷ solar mass supermassive black hole, and the binary about a parsec away. And this is the acceleration then. So this is a signature, I think, that's detectable with LISA for the stuff we're discussing this week, as long as the object is within a parsec of a nucleus of a 10⁷ solar mass black hole.
How much do you suffer if it's further than a parsec?
Well,
Trade microphone. Please repeat your question.
How much do you suffer if it's further than a parsec? How does it feel?
Epsilon goes linearly down, and so I think beyond a few parsec, it's not going to be detectable, or you need super high chirp mass.
Then the time to coalescence goes. If you have a really high chirp mass, the time to coalescence goes like chirp mass to the -5/3, and so then your binary just merges really quickly. The chirp mass is really large.
That's also true. You have less time. Yeah.
I have another question. So you said that the orbital timescale of the binary around the supermassive black hole is how long?
I think I remember 10,000 years.
10,000
or
years.
at a parsec. We can do it quickly, but.
So then the idea that I had was that if you could be in a particularly really optimal scenario where you have a red shift and a blue shift, right? You might be just going through this particular phase.
So, so I should say, if you go back one slide, the paper, the other two papers which I listed. Sorry, not go back. The other slide, the other side of my slide. So this Lisa Randall considered the case recently where you put an object extremely nearby a supermassive black hole. So if you're so lucky that you have such a case, then you can have much more dramatic. So these are very small redshifts. The redshift I'm talking about, which I consider realistic collocation of the binary, relatively far from the nucleus. The redshifts are like 10⁷, 10⁸. So you have, let's say, one or two cycle changes over a million cycles. These papers considered a much stronger effect. Actually, maybe Benza should describe that, because I've never calculated that, but then you can have, of course, order unity changes to the waveform.
Yeah, so here Zoltan's idea is that you can just measure directly the acceleration, but then of course you don't know if it's exactly due to a supermassive black hole orbit around the supermassive black hole or something else.
Wait, what else?
That's your paper. But
I think it doesn't prove there's a disk, but I don't know how to get such a large acceleration any other way other than being near a supermassive black hole.
What about if it's kicked out from a triple disruption? Velocity binary.
But then it's not going to accelerate. It's going to get constant. These were R.
So if there's a stellar mass black hole nearby, but closer than a parsec, like say, have a stellar mass black hole at 10⁻⁴ parsec. Can it not generate the same type of acceleration?
Then I think the problem would be it's not going to last for years at constant. Then you again get some dramatic order unity effect. If you have a third perturber extremely close by, it's going to be some order unity effect for a short time.
Yeah. So in our
actually, I do claim this is a proof. If you see this term f to the 13/3 term, it's a proof that your object was near a nucleus. Maybe I should wear that hat, but I think the problem is potentially the degeneracies with the other parameters.
Right. So
of the
one case when you don't have degeneracy is if you're even closer in, right? So if you're at, let's say, a 10-year orbit around the supermassive black hole, then of course, like S2 star around Sagittarius A star, in that case, of course, you don't have any degeneracies because you can just see a repeating signal. But maybe that's very unlikely, right? That's your point.
Well, maybe that's a good thing to discuss. That would be, I think, much better for us if there was a binary so close to the nucleus. So do people think that's possible?
But the 10-year orbit is not that close. It's like 10 to the 4 Schwarzschild radius, right?
Well, I mean, just taking like Amy's and y'all's models, I mean, that puts a binary at what, 12,000? So that puts it at what, 600 AU around a 10 to the 8 solar mass black hole? That's what, a 500-day orbit? So it's going to do like 4 or 5 orbits within LISA. That'll be a redshift of 0.03 change or 0.04 change just in the velocity alone. So you see it go up and down about 4 or 5 times during LISA's observational window. I mean, that's pretty easy.
Get that man a Yankee sound.
Do I get to keep it? I've actually really wanted one of those. I want to see how far I can get in Boston with one.
Yeah.
You have a more optimistic hat?
Dan says that that's what his slide is about.
Okay.
But maybe Ben said it should go first because he's talking about all of these things.
Yeah.
Indeed.
Oh, I changed my slide.
Oh, you did?
Okay, we'll go to Dan then.
I was just, I might need a few Yankees hats for this slide though.
Yeah.
Okay, pass Dan the hat while I bring his slide up, please.
Hat, microphone, and pointer.
Oh, wow.
That's not right. That's Andrew.
Paraphernalia.
Okay.
How do we get, hold on, this one.
And you got a
Okay.
This was just going to be quick to think about. I usually don't wear bald caps, so it's kind of weird. But okay, yeah. So I was thinking about smoking gun signatures, and I was actually making this plot that I'll explain in a minute for a different project. But what this plot is looking at is gravitational wave frequency on the left.
Where'd the laser pointer go? Does
Oh,
anybody
I think I
have
have
it?
it. All right.
Oh, okay.
There.
All right.
Okay, right, so let me just back up and say I'm thinking about, of course, these stellar mass binary black holes orbiting around a supermassive black hole. And I just made a plot here where we have gravitational wave frequency of the outer orbit, the low frequency orbit, versus the mass of the supermassive black hole at the center. And I've just plotted kind of a rough signal to noise ratio calculation for the outer binary, so the low frequency binary.
So this is a stellar mass binary around a supermassive
Yeah.
black hole.
Right, and I'm only looking at the low frequency gravitational waves here and saying, are they detectable by LISA? I've just chosen this just for an example, a redshift and a mass ratio for the stellar mass to supermassive black hole binary. So at the moment, right, you could just say that if you have a 10 to the 5 solar mass central black hole, then there's a mass ratio between that and the outer stellar binary of 10 to the minus 4, so you have a 10 solar mass total binary orbiting the 10 to the 5 solar mass black hole, if that makes sense how to read this.
So I have 2 different gravitational wave signals that I need to take in. There's 2 gravitational wave signals to take into account.
Yes.
One from your stellar mass binary and then one from this longer.
Exactly, and
orbit.
I just wanted to ask, can you ever get both of them at the same time?
I think you can do it with the Einstein telescope.
Or even with, so I was asking LISA plus LISA, so get them both in LISA, and Emery plus the over to the outer one, or LISA plus Einstein, LIGO, DESIGO.
I can't remember the author paper right now, but I heard about binary Emrys. So you could do an estimate of the radius at which a binary would be tidally disrupted if it was close to a supermassive black hole. It's like 10 Schwarzschild radii, which is also where you would start to detect the Emery. But you can actually, there's a possibility that you could be a binary Emery before the stellar mass binary is disrupted, in which case you would see an Emery signal, but with some extra frequency mode from the binary orbital frequency, and then it would disappear.
Yeah, I think that's a good point. And I think a paper that looked at an idea similar to this was Babak et al. 2018. I don't know if you've seen it, but it's a recap of Emrys, like with an E, for in the LISA band. And I think that they, in fact, do go over something similar to this. One other thing that I think astrophysically is really interesting is when if you have a supermassive black hole binary system overcoming the final parsec problem, you are going to get a lot of these scattering events that are happening around it. So during this stellar hardening phase or equivalent, you could have black holes in there. You might get an increase in these kinds of events, which could be really interesting gravitationally. Even before the black holes themselves become interesting as gravitational wave sources, these scattering events would be precursors almost to the eventual LISA or PTA signal.
The other thing to throw into all of this dynamical discussion is you also have the effect of gas drag on the waveform as it's going through the disk, right? So the binary itself will have a gas drag on its waveform, and then the large scale, like
Right.
it's cool.
But this only seems to be possible timescale wise. I was looking. You can only have it seems that you can only have a detectable outer M-rate plus a inner, higher frequency source if it's sitting at this so-called inner migration trap at 25 Schwarzschild radii, which seems pretty hard to do, right? Yeah.
Yeah.
So, right.
That change.
Because otherwise, the time scale for mergers is quite short.
Yeah.
So that's one thing that seemed to be interesting to find from this. So just as a guide, then this yellow line is kind of detectable by LISA, and this orange line is 25 Schwarzschild radii distance. Okay, and then but the second thing is I also have drawn here white lines, which is the orbital velocity of that guy in units of v over c. So, I mean, you can even just estimate this without the plot. At 25 Schwarzschild radii, the orbital velocity is 1 over root n, right? So it's going to be 1 over 7, something like that. So it's large enough that you might have a large relativistic Doppler boost of this, of whatever emission is attached to this orbiting binary. Yeah.
So I think, even if we're wearing the pessimistic hat, I think it would be really interesting to do a rates calculation to see if you can find, even if you find just one of these systems, what can you learn? Because I think this could be a kind of golden opportunity in that sense.
And I've been thinking of a few different things that you can learn, which I don't think we need to talk about here, but it's first seeing how many you might be able to.
Exactly, and if the answer is a few, then maybe the physics that you can extract from those few observations is motivation enough to just really kind of flesh out the problem.
So I would flip your hat to the Yankees hat, because if the migration trap is not strong enough to hold it, so basically if we're wrong about the density profile in the disk, then binaries, massive binaries in particular, are going to migrate faster than anything else. So you could very well have a binary MRI running through the gas at this sort of scale. So it's going to be changing, its A dot is going to be big, but it'll move through the band and you'll, right? So yeah, you could have a binary MRI coming in and, right?
Sorry, I'm really slow. I'm trying to just ask you a basic question. So this is a stellar mass binary with in the LISA case, there's a stellar mass binary which is very close to the supermassive black hole, and their frequencies are similar or within an order of magnitude. Or did I miss something?
There's a whole range of frequency ratios based on this. There would be a whole range of frequency ratios based on the separation of the stellar mass binary, and that is truncated on the small end by tidal disruption.
Right, this is what I was wondering. If you want a stellar mass binary whose orbital frequency is in the LISA band, and then you put it near a supermassive, so the orbital frequency around the supermassive is also in the LISA band, and they cannot be very far. So then tidal effects, I think, will actually mean that the orbit of the stellar mass is not a circle or an ellipse. It's going to be actually distorted.
Yeah, that's
noticeably, because, well, first of all, you don't want it to be tidally disrupted by the supermassive, but even if it's bound, the orbits within the Hill sphere are not, circles, unless you're really, really deep inside.
Yeah, so you have a tidal.
Maybe it's in all invented space, actually.
But you could have that'd be interesting. It'd be like when you have a neutron star tied, you have an F double dot change, so you'd have an extra change in the chirp, perhaps. from,
See it in the waveform.
yeah, right. With a, if you can measure F double dot, I think. then
See
you
the
can
one in
do
your
it.
paper, the
It's not
Mayron?
in the paper.
Write a new paper.
Okay.
It's a weird it's a weird orbit. It's this teardrop shaped orbit.
Yeah. Yeah.
One more thing after
If the frequencies are very close, then of course the binary will be disrupted because the disruption criterion is that the frequencies match, right? Yeah.
Yeah, so, I mean, the idea is you could have the Emory in the lower part of the Lisa band and the binary, the stellar mass binary in the higher frequency part of the Lisa band, but, or in LIGO.
Just to restate it again, so you want the frequency of the stellar mass binary to be higher
Yes.
than around the supermassive. So if it's, let's say, 10 times higher, I think you still have a 10% deviation in the waveform. for
Yeah, I
the
think
stellar
that's
mass binary.
really interesting, yeah. Yeah, I think that's an interesting point. Did you want to say one more thing? I just had one more point in this slide and then I can stop.
Yeah, I think one of the problems could be that if you extrapolate this source backwards in time, you would disrupt the source not long before this happens. So I don't know if these types of sources can actually form realistically. But
I didn't quite get the time reversal argument.
if you think about how the sources got there, got to this point, and extrapolate where they came from.
I see.
Um,
So you're saying if you have to migrate.
So the stellar mass black hole binary in spirals more quickly than around the supermassive black hole. So you would reach the disruption criterion in the past very soon. I mean, not long before this observation is going on.
But Ben, if you're forming them in the resonance trap as opposed to migrating them in, you're by definition going to only form ones that can form. I mean, it's like the hard-soft boundary, but with gas.
Okay, well, this is the kind of discussion I wanted to start. I just want to make a final point that, again, since these orbital velocities are so high, and if we do find something in gravitational waves in this area with these orbital velocities, then it might warrant an electromagnetic search to look for a possibly faint but periodic signature from relativistic Doppler boost and lensing, because we know the frequency, so you can narrow in on that frequency and have a better chance of looking for something. But lensing can create magnifications that are...
But if you're optical thick,
Right, so, but until we solve that problem, we can look if we have the gravitational wave, so we should solve the problem first.
I think, well, the takeaway would be that Lisa may detect these, and the exciting part is you can probe disks. So if you wanted to see what could be done in the next 15 years, it would be to understand this effect more, which is something I work on. Maybe some implications of the AGN channel for LIGO is that, of course, if you see these, then it implies that this is happening. Maybe we'll discover that before. It would imply that migration is sufficient to bring these black holes into the disk or into the inner disk where they would eventually merge or at least enter the Lisa band. And also something we talked about over coffee was just production of binary extreme mass ratio in spirals. So maybe you still have a binary when you enter the Lisa band, and that's something we're thinking about. I think that was all I wanted to say.
Very quick comment. I would maybe be a bit more optimistic about LIGO, because depending on the interaction of the binary with the embedded gas, if you're driving eccentricity, the eccentricity might show up in LIGO. And so we can still test these embedded stellar mass black hole systems.
Right, it depends on if that
pump it.
eccentricity is different than those produced in the field. Or the eccentricity distribution of the gas embedded binaries might be different.
Right, so it depends what is an AGN, right? What's it embedded in? Yeah, but again, we can test it.
There's a feedback as well, right, where the gas
One moment.
interactions can drive eccentricity.
Right.
So it's also a coupled system because the gas interactions can make the binary more eccentric. Are you agreeing with me?
Yes, and if you make the binary eccentric, as has been shown, if you make the binary eccentric at all in band, we will be able to do fantastic, awe-inspiringly wonderful things. So if you do it, we will know a lot.
Yeah.
And it doesn't take many.
You're talking about for LIGO.
Yeah. Oh, it would be fantastic.
So they go hand in hand, and I think that we should remember that these are not decoupled things.
I think.
But I just don't know if the eccentricity, you couldn't tell it was due to gas. It could be due to just the binary formation.
Yeah, sure,
of the
but
environment.
the present, well.
Well, actually, I'm not entirely
Yeah,
sure.
no,
If
that's
it's
good.
really highly eccentric, I'm not entirely sure if the lever arm is entirely going to decouple it in the LIGO band.
Yeah.
So we think more carefully about
Thinking
that.
about
It would be,
I think-
as I said, awe-inspiringly wonderful things can happen. However.
The interesting thing about eccentric sources is that they spend more time in the LIGO band. So if you have an eccentric source, you can have you can have a stellar mass black hole merger in the LIGO band for hours if it's eccentric.
Yeah.
Yeah, but the SNR isn't that high in the LIGO
The
band.
SNR.
Hours?
Yeah.
No.
It's not yeah, the SNR is not as high, but
That's also why Lisa is better at
So, whoa. You're really good at throwing those.
I
So-
agree, the SNR might be a problem.
If you wait long enough, I mean, you don't need a lot of SNR.
Okay, I think this actually answered my question. Never mind.
So I just have a question. Sorry if you already discussed this. What is the gas density that you're assuming here?
So the simulations, again, they're scale free. We don't assume a disk mass. So you can actually rather ask at what density is this detectable, right? I think so for the simulations, this is okay because the gravitational wave torque is so much stronger that it's not going to affect the inspiral enough for you to need to include it. It's basically this extra perturbation.
So I would say, I would argue, and I think this is the thing that Zoltan and I were sort of hashing out yesterday is the issue, right, when you're doing a circumbinary disk that's scale free, you're assuming that the disk is implicitly the right disk for that central mass. So it's only scale free
You're assuming it's much less massive than your inspiraling
correct.
object, yeah.
But in an AGN disk, that's not obviously true. For 2 10 solar mass black holes embedded in a very and also the scale height is not going to be right? So the one thing that the caveat that I would have about this is that this is a minimum. I would say this is sort of the worst case scenario in some sense for detectability. But if you put more mass in there, then you're going to have more drag and you're going to have more dynamical friction
Which makes it more detectable.
Which makes it
but
go
still, I think
faster
this
and
is
more
a-
detectable, yeah.
This is 1,000, was scaled to 1,000 solar mass black hole, inspiraling to 1,000,000 solar mass black hole.
Right.
The amount of mass in your inner disk
Yeah.
is much less than 1,000 solar masses.
Right, but I'm saying in
That's
an
based-
AGN disk, if you have 2 10 solar mass black holes embedded in an AGN disk, then you're going to have more mass closer in. Or you may have, so in an unperturbed AGN disk, right, you're going to have higher densities and more mass, which is why you might be jamming, substantially super, like whether it'll accrete or not and what the feedback looks like, but you can stick a lot more mass in there.
Yeah, so I would say the migration torque here that I'm plotting is scaled with a density that's taken from an estimate from beta disk models, which are pretty dense. In the inner regions, it's like 10 to the 7 grams per centimeter squared or something like that.
10 to the 7? 10 to the minus.
Minus 7, sorry. So, no, yeah. So, if you were to
surface.
surface density, 10 to the 7
square centimeter.
No, 10 to the minus 7 would be very
Oh, 10 to the,
low.
yeah, sorry, 10 to the 7, oh, sorry, it's surface density, so 10 to the 7 grams per square centimeter. Okay, fine, yes.
Okay, yeah.
yeah,
Okay.
if you were to scale that or just multiply that by the area that you have when you're in your inner disk
Yeah.
in 10 Schwarzschild radii, it's not that much mass, total mass.
Yes.
Either way, yeah, right. So if you have more mass, this effect is likely more detectable.
Right, yes, no, I'm saying, so for the so yes, I'm putting the optimistic hat on and I'm saying that, but then modulo, of course, this is so yay, and maybe even more yay,
For lighting.
except feedback. So maybe not
Oh,
yay.
yeah, of course.
So that will also mess with the gas density, so that's
So there is like some torque within the hill sphere we talked about that would be definitely affected by feedback. That's comparable to the amount of torque that's exerted by the disk outside of that region. It's just a different sign.
Yes.
Note that for an isothermal fluid, this captures all the overdensity that you get. So the real thing is when you're not isothermal. Like, so the density enhancements are here in these simulations for an isothermal fluid.
Right.
But when you add in cooling and et cetera, then you can ask if you get anything denser.
But how effective cooling will be depends on the optical thickness.
And the geometrical thickness too. The optical, but the thickness.
Yeah.
So it's possible we just do more studies to understand how strong the torque is, but given that, you can then plug it into these calculations that are done to estimate detectability. Just separate part of the problem.
Cool. All right, you pass this to that side. There also has some multi-sided slides.
No, we can just
Yeah.
we can just do the first one.
Oh, we can just do the first one.
Yeah.
Depending on who's This was a 4-sided slide.
No, it's okay.
Multi-dimensional.
No one has 6 slides, right?
Yeah, that'd be 6 here.
Yeah, we've already discussed the other 3 slides basically. So and
Mike.
Like this mic on. Oh, hold it closer to you or put it on your shirt. Here's the pointer.
okay.
Where's the other one? Okay.
Yeah, so is it on? It's on. Yeah. So yeah, it's basically, I didn't know that Andrea would discuss her slide, so this is basically the same thing. This is a paper in 2011, or 2 papers we've written. And so the nice thing here is that we're showing in a parameterized way, a modally independent way, what is the detectability of the torque exerted by the gas disk using LISA, using the gravitational wave signals. So you're assuming that you have some model, which could be type 1 migration, type 2, or whatever effect the gas generates, which is parameterized by 2 parameters, the amplitude of the torque and the radial dependence, which we assume to be a power law. And so B exponent is one of the parameters and A is another parameter. Depending on what the size of these parameters is or are, sets whether or not you can detect this type of perturbation with LISA. So here we're showing 2 examples. In one case, it's a 10 plus 10 to the 5 solar mass binary, which starts from 25 m basically of the orbiting around the supermassive black hole, and ends at 16 m. And depending on what you assume for the torque, so here we're looking at 2 types of disks. Shakur-Yasuni have alpha disk and beta disk, where the viscosity is proportional to either the total pressure or only the gas pressure. And we're also looking at type 2 migration from the Sire and Clark paper for different types of disk models. And depending on which of these you choose, you get basically these points here. And this line shows the critical curve where LISA can detect the source. So if the amplitude is larger, so if you're in this region, you can detect it. If you're here, you cannot. And so LISA will test this. So if you're here, so if there's a perturbation to the signal and it's larger than this amount, then for the A and B, then you can detect it. So it's basically the same thing, except we didn't have a correct model.
So I just have a quick question, so if you're at 25, so 25 M, so you're at 50 RG. So the mass of gas in the disk is going to be really small, and so this migration timescale should be very long,
It's,
right?
it's relatively long compared to the observation time.
Right.
But the point is that LISA is an extremely sensitive measurement of the phase. So even if you shift the total phase by a relative amount of 10 to the minus 4 or 10 to the minus 5, you can detect this. So the migration rate needs to be 10 to the minus 4 of the observation time. Basically.
I just wanted to help out people who are not used to thinking about distances in terms of m, that m is 4.9 times 10 to the minus 6 seconds. And we think, well, I think a lot of people who do gravitational waves think about m's in seconds. And you can also think about m's in terms, you can convert the seconds into the speed of light, but this is like c equals g equals 1 units. So people are a little bit confused about that. That's how.
It's a Schwarzschild radius, basically.
Yeah, sure, but like
So two
up to a factor of 2, yeah.
Yeah, 2 or yeah.
But for sure, just I don't know if everyone already knows that, and maybe some people are afraid to ask. So you can think about that in different ways.
Yeah.
Two M is RS, right?
M is.
It's a Schwarzschild.
No, I think it's RG.
that?
One M is
that-
4.9 times 10 to the minus 6.
Exactly, 4.9 times
GM
10 to
over
the minus
C
6
cubed
seconds.
is 4.9.
For what size black hole?
It doesn't matter, it's still free.
Yeah.
So now that we're not confused anymore.
Yeah, thanks for clarifying that, Kara.
Thank you.
Thank you so much.
We're all on the same page. You're welcome.
Yes, think of them as RG.
That's as far as they probably need to
The
go on that.
yeah, the gravitational radius is.
So that's it. More.
Yeah.
That's it. More slides. There's more question.
Yes.
Yeah.
Do you have a question?
Sorry,
or
I
are
was
you
thinking
just
with my
thinking?
hands like.
Okay.
It's your Italian side.
All right. Do you want to show more or?
Yeah, no, I think it's fine. Yeah, so this is, just to reiterate, we already discussed this on the first day, but there are a few smoking gun signatures you could look for, and of course, yeah, Zoltan already mentioned this. And this is what you've pointed out then during coffee. So in principle, you can have a source which is orbiting around the supermassive black hole, and this source can be, the orbit around the supermassive black hole can be in the LISA band, while this orbit can be in the LIGO band. So you can have this binary, both of which would be detected coincidentally. And so this curve would be the curve, this would be the outer orbit, and this is the inner orbit. So in this case, I think it's not a supermassive black hole perturber, but it's just a tertiary stellar-mass black hole. So here you would have a merger of this guy in the LIGO band, within a minute. And then later on, it would merge, the remnant would merge with the third object within 7 years. So in principle, if you detect this, of course, you would know everything about the source.
Yes, you could also have the smaller binary be eccentric, and then it would be bursting in the LIGO band and last for longer, apparently?
Yes,
Okay.
yes.
Yeah, because I suppose at some point you would expect Kozai of oscillations to make. Oh, but okay, let's not get into that. Yeah.
Yeah, so this is the other slide. So the Kozai-Lidov oscillations can also be detected in principle with LISA. So you can. So here's how the eccentricity evolves as a function of time. So it makes these extremely large spikes, and during this this is on many orbital time scales. But you can zoom in on one of these spikes, and here the eccentricity increases and then decreases, which leaves an imprint in the waveform. So this is how the waveform looks like initially, and then when the eccentricity is really high and or low, and then as the eccentricity increases, the peak shifts and then it decreases back.
I have a question. So the tertiary in this case is the SMBH? Is that the idea?
So this is specifically calculated for an SMBH tertiary. Yeah.
Right, but the mass in the disk is going to act as a right. Are you going to damp the the eccentricity inclination exchange?
Maybe, yeah. So this calculation ignored the possible effects of gas.
So this is basically independent of gas. Right.
Free-body
Yeah.
problem in vacuum.
Yeah.
But if you have gas, then the common knowledge, I think, is that if you open a gap, then you increase the eccentricity. If you don't open a gap, then you decrease, right? I don't know.
There's this number of 0.6 that floats around in some of the
0.6.
hydrodynamic simulations.
Alt.
Yeah. I mean, I don't like to say numbers exactly when we're talking about hydrodynamic simulations of circumbinary disks, but in some of the simulations I've done and some that are published, there's this magic number that seems to show up that eccentricity grows to 0.6. And I think that's has to do a little bit about what Andrew talked about before, about the secondary hitting the cavity wall, but also the cavity shape itself becomes more circular for higher eccentricities. But
didn't you and Alberto Susanna write a paper that found this as well? With the supermassive black hole binary systems, that there was a peak in the eccentricity at around 0.6.
Yeah, I wasn't in that paper, but yes, Alberto has this paper.
Yeah.
There are many papers.
You pass back to Fabio.
So in the case in which the binary black hole is not fully embedded in the disk, I think that actually the presence of a disk could help in getting the binary to merge. And this was shown in a recent paper we published with Cristobal Petrovic. And so what we showed is that it's very hard to get a Lidov-Kozai merger in a spherical star cluster, because you really need to start with an inclination of the outer orbit with respect to the inner orbit that is very, very close to 90 degrees, otherwise you don't get a merger. But if you have any axisymmetric perturbation to the potential, then the outer orbit is driven by this by the non-spherical component of the potential to a different inclination. And so you can get a system that is initially not in the Lidov-Kozai regime into the Lidov-Kozai regime and get a merger. And so I'm not sure about the case in which the binary is fully embedded in the disk, but if that's not the case, then actually the axisymmetric potential that is due to the agent disk could actually lead to an enhancement in the merger rate due to this process.
Please.
So I mean, would it be fair to say that in that circumstance that the disk itself is acting as the third body that's driving the... Well, it's a fourth body, but yeah, okay.
So the third body would be the black hole that is inducing the Lidov-Kozai oscillations in the black hole binary, and then there is a perturbation on the outer orbit of the binary on the supermassive black hole due to the disk.
Oh, I see.
Which leads to an inclination change of the outer orbit with respect to the inner orbit. Yeah, so you can change this inclination.
Oh, so you might actually have something even that's embedded in the disk.
So
or crossing the disk, inclined.
Inclined even if it's in the disk.
Yes.
Does it draw a
Yeah.
picture?
This is
Yeah.
a good code picture.
Not here, I'll find it.
So
I think the point is that
Well, you need to be outside the disk for this to work, right?
Do we have
Because
any
if you are
markers?
exactly on the disk, then there is no torque. on the
so the disk changes the outer orbit inclination and
Very.
helps to.
and then right.
Yeah, that's the outer orbit, and the outer orbit changes, right, because of the disk, and that can help to put the binary into the regime where the quasi-Lidov effect is most efficient, right?
Then there's this additional effect that Zoltan mentioned earlier, right? How the black hole will also, raise tides on the binary, and so the orbit there is also perturbed by.
Right, Zoltan mentioned this earlier, that the binary's orbit, even if it were circular when it started, is now this teardrop shape due to the presence of the supermassive black hole. And so this is an additional wrinkle, I think.
So the other interesting thing about this is that you
Pass the microphone back to Pat.
actually it's not the so it's just the nodal precession of the orbit that changes the inclination. So the orbit is just
Right. I'm trying to do better, Richard.
well,
Richard would do a much better job.
No. Richard needs a break.
I'm about to
The
go on
understudy.
before.
Stop letting yourself down.
Anyway, so the rate in this case would be, we find, would be increased by 2 orders of magnitude, even with respect to the case in which there is not, in which the spherical cluster around the binary is spherically symmetric. I like the math.
Just on the E equals 0.6, right? So, this raises an issue that came up yesterday. If you're fully embedded in a 3D disk and you're getting these kind of flows coming in and smacking each other at different angles, I don't know what the eccentricity is going to end up as, right? So if you have a net plane to your simulation, sure, I can see eccentricity pumping, but if you have these flows coming in at various angles, again, this is why we want to understand how to move forward with this.
I think the 0.6 corresponds to the coplanar case, right?
Right.
And maybe the streams are neglected in those simulations, right? That you mentioned. No? They're not included?
Basically, also a number that I found recently for the full.
Okay.
I should say that Moody paper that I mentioned on Monday does do a case where it's non-aligned. So if we could look at that, it's in 3D, so it's
okay.
Yeah. Cool.
Last comment before we switch.
Oh, all right. I was wondering about one thing, and I don't know if it was already mentioned, but EM counterparts, right? I mean, like one of the things that that could happen is that so what we have mergers, right? Most of the mergers will actually be of low mass, right? Of lower mass that can be seen actually with LIGO nowadays. But these mergers are happening in a gas disk. So when it happens, you have a burst that will change the angular momentum of the gas, and then it will lead to accretion onto the SMBH. Wouldn't that lead to a burst that could be seen? Yeah. So the point is, even if we have many mergers that LIGO cannot see, you will have EM bursts that can be seen.
In the AGN disk?
So I agree with your point. So if everything is muffled and we can't see in and it's all happening in the midplane, and things don't get out, you'll have these pulses of low angular momentum gas. So whether it's a supernova that's kind of muffled and blanketed or a merger that transfers angular momentum to some gas, you're going to end up with a pulse of low angular momentum gas that's going to fall. In the case of a supernova, right, you'll have a wind blowing into the surrounding gas. Some of it's going to lose angular momentum, right?
Okay, so the stuff that's backwards.
Yeah. And so you'll just get a net drainage onto the SMBH. So some of the variability that we just regularly see, some of the pulses could be from events deeply buried in AGN disks, right?
I'm going to get the Mets hat, though, because Mets. Pessimistic. Bad. Very bad. This is a pessimistic hat, though, but the problem with that is that locally you're going to change the angular momentum, but if you're embedded in a pretty thick gas disk, the viscous timescale at the radius where this is going to happen is probably long. And so you're going to go a little ways, and then it's just going to get mixed. And then, there's not going to be an immediate it's not like, oh yay, we saw the LIGO event and we turn our telescopes there and then we're going to see the black hole eat an extrasolar mass of stuff in the next, few days, because it's going to take way longer than that for the signal to propagate in to the SMBH.
But if you cancel the angular momentum, things will drop down in free fall.
Yeah, it'll spiral.
Well,
down.
no, because there's lots of gas inside it.
Yes.
You still have
Depends on how much.
You still have the inner disk that you have to fall through, which will then
That's
just
correct.
spin you back up. So
But
it's a quantitative question. I think he's estimating a large number, she's estimating a small number.
And we need to calculate for that.
But it is ultimately a quantitative, not a qualitative question.
That's correct.
All right. While we debate about which hat to wear, we're running out of time, and it is Richard's turn to. I don't know if he's dancing or if he's just going to talk. But,
I might dance just for fun.
all right, his slide is up.
No, by this point, you've heard all of the ideas, and so when I wrote this down, which I put together in all of 5 minutes to start the session, I was not surprised to see that people have talked about everything in the first half of this, so that's great. No. What just happened?
What have you done?
You're hitting.
Oh, I hit play. Where's the?
There you go.
There we go. Okay, so gravitational waves are cool, and I'm going to take off my theorist hat and put on my observer hat. Which is going to be
We don't have one of those.
Where's the Yankees hat? Give me the Yankees hat. Okay. All right.
There you go.
LIGO is on. It's really sensitive to high mass black holes, high mass ratio black holes. The fact that we haven't seen it reported any yet is not an indication that we're not sensitive to that region. We're really sensitive to massive things. And we don't lose sensitivity in this region. This is a synthetic plot that I made up, or my student made up. And so the data is going to decide. The data is going to decide soon. We'll have, 50 next year? Then sensitivity just keeps going up and up obscenely after that, a factor of 10 here and there. A+ was just funded, which gives us another factor of 7 on top of the. So we're going to have thousands per year in the very near future. 1,000, yeah.
That's alarming.
Yeah.
I mean, wonderful.
Yeah, but and this is something that I think people don't fully appreciate. Thousands per year. So unless the event rate is, smaller than 1 over 1,000 of anything else, they'll be able to say something. So that's really constraining. And we're most sensitive up here. So so a event rate of 1 over 1,000 means the stuff over. Yeah, this is the happy dance time.
Yes, yes it
is. Right. And so, and in some of these parts of parameter space, finding something above the PP instability gap, lots of things above PP instability gap, IMDHs. Yeah, we can do it. In some corners of parameter space, if we get high mass ratio or eccentricity, we can do fantastic things because the signals are long. So again, the data is going to tell us really soon. And we already have tools that are set up that are ready to go.
When are we going to get our first 1,000?
I think that's 04? End 04? I have to double check. Early 05. You want to say something? You might remember.
No, what I meant to say, then we are going to get the 1,000, you mean A+?
Oh, no, that's per year.
23, 4, 5, yeah.
Well, I mean, no, but integrated. I think integrated we get it before A+.
No, but advanced LIGO.
Yeah, advanced LIGO.
Sensitivity.
Design sensitivity is.
But let me add
Listen.
something to that. Let me add something to that, what help Richard is saying, that I know you have very high hopes and we are the most sensitive for the higher masses, but there is a limit to that, and this is not official, nothing like that, but I have some doubts of us reaching the low frequency sensitivity of advanced LIGO. So if any of your models really rely on those.
At what level is at what?
I am saying I have doubts reaching it below 20 hertz and anything what we quote on the design.
What mass?
Oh, well, you're asking for masses. So.
about what mass? Come on in, come on in.
Hi, so this is Jim Simons. Yes.
Simons.
Makes the Simons Foundation and the Flatiron Institute possible. So welcome, Jim. So we're having a workshop on black holes and accretion disks.
Have you found any?
Yes.
We're working really hard.
So, most of you.
Give him the mic, please.
Give him the mic.
Oh, yep.
Sousa?
Sousa, Mike.
Give him
Can you give him the mic, please? Thank you.
So, most of you are not part of Flatiron, is that correct?
Yes.
Yeah.
Correct.
All over the world.
From all over the world for this workshop. Who is from Flatiron? Raise your hand. Just 2 people?
Several people have been here and stepped out.
I see. I would have thought, well, anyway. So you've come from all over to discuss black holes.
Yeah.
And how long is this workshop?
3 days.
3 days. How is it going?
Excellent.
Fantastic, huh? Really good?
First workshop on the question we're asking.
Yes.
Ever.
Okay. Well, his
Question you're asking.
The question we're asking is, how do black holes that are entrained in the accretion disk of a quasar around a supermassive black hole behave? Because they behave like planets do in protoplanetary disks. And so we're drawing that analogy.
And they could account for anywhere from 100% of the LIGO detections to date to 0% of the LIGO detections to date, based on our current astrophysical understanding. And so we would like to figure out which one of those it is.
But it doesn't matter whether it's 100% or 0%. We win either way. We learn about the gas disks, or we account for all of LIGO.
Well, wait a minute. Now, the first LIGO incident was 2 black holes spinning around each other furiously and merging.
Right.
But there have been quite a number of other.
That's what we're discussing. That's what we were discussing as you walked in. Was how many do we have, and when are we going to get to 1,000?
But
which seems
look,
to be
we
within
had
a few years,
2.
and what the upper mass limit.
But what
for
about
those
the
detections will
neutron
be.
stars that crash into each other?
That's also going to happen in AGN disks, so excellent question.
So we-
That's another workshop. We're going to have another workshop.
on that, yes. David Spergel calculated the value of the gold that was produced by that interaction. And it was, I don't know, it must have been 1,000 times all the money on Earth, if not 100,000 times all the money on Earth. There was a lot of gold, if you measured it in dollars, that was apparently produced by that interaction. Okay, well, I'm not gonna, I think you should go on.
Jim, I think it'd be interesting to see how many people here that are not at the Flatiron, but at our local New York universities and institutes.
Yes.
Right?
Yeah.
So
Everybody in New York.
NYU.
Okay.
New Yorkers, raise your hand.
Okay, a lot of New Yorkers, but there are a whole line of foreigners over there.
Californians.
Yeah, Massachusetts.
Kazakhstan,
Los Angeles,
Italy.
Los Angeles. That's great. That's great.
Hungary,
Yeah.
Japan.
And who's from Japan?
Well,
Oh.
he's working in Hungary
I
now.
can see that. I mean, you look Japanese, so I'm not surprised you're from Japan. Okay, well, you guys carry on, and I hope you'll get all the answers by the end of the day.
You're kicking us out at 4:30, so we better.
We gotta get back to work.
Right.
I
So-
still am working on the mass question, though. What is a modest upper limit to the mass that will be detectable? Is it
What do you
100?
think, total mass 100-ish?
I know, a few hundred. That's plenty.
Few hundred-ish, you say? And I have a problem with distinguishing them from glitches, right? So it's half a cycle. Yeah.
Okay.
No, but what I said that a lot of you guys here doing theory, just think about we may not reach that design sensitivity below 20 hertz. I have some doubts, but this is not an official LIGO saying it's
But
me.
it's sensitivity of, even if we could get 100,
Yeah.
that would already
Yeah,
be,
I mean you're gonna get 100.
that would
It's
already be
729
pretty.
detector frame is
Oh,
above.
sorry.
I mean, we already have.
You already have a paper.
Yeah, we already have a paper with an example of.
Yeah, I know.
With this, that, so it will be done.
So what's
'Cause we
your
have-
take? What is the highest?
Well, we have one with detector frame masses of 130, whatever 170729 is.
Yeah.
So demonstrably, and that's the merger is about, I think, a few hundred, like 100-ish some hertz. And the problems come when we start having to trust the data below 10 hertz is really problematic. Going down to 5 hertz is crazy, but what we can in principle do
But
it.
we have
Yeah,
a notch at 14 hertz, right?
that's fine. It has.
So nothing below 14 hertz is gonna be because there is. Well, so we have calibration lines right there, right now. So, but yeah.
And what's
Alright.
the best error box that we can expect?
For
Best
scope?
error box. 5 degrees. Any detectors, anything better.
Then
Position reconstruction, or what is that what you're asking?
for a 100.
Tripper detect, no, oh, you're asking for the 100? No, I mean, for tripper detector data or even more.
A few square degrees.
Yeah, 5 square degrees, that's what I'm saying.
Yeah.
Andrea has a question, and then Carl, and then we should consider eating lunch.
Might be pessimistic because I know it's a problem for the LISA sources, but I'm not sure for LIGO. What is the status of intermediate mass ratio waveform templates? And could these events be happening and we can't detect
We
them?
can tell that they're intermediate mass.
Do we? I thought those were really hard to.
They're
to
really,
get through
so
once
the
we
GR
learn
is
we
hard
don't
once
have
you
it
get to like
method.
100 to 1. It's a computational challenge.
Yeah.
But if you have something that's not, so the question is so it's a question of balancing how precise could you get and how precise do you need to get to answer the
To
question.
get the parameters.
I mean, if you just want to know, it's really, really high mass ratio is about this, and there's going to be some degeneracies, I think that a lot of the astrophysics you can do even with crappy templates. Now, is that the best possible template that you can do? Absolutely not. There's a huge amount of effort that needs to be done for LISA and for like that. But for an eccentric binary, for example, if you have something that's really ridiculously long and had lots of pulses, and then gets fairly circular and then merges, I mean, okay, yeah, doing phase coherent matching in the strong field, we have lots of parasitic passages and lots of higher modes. Doing that right is tricky. You'll have some biases. Will you know it's eccentric? Yes, you will.
And you will know it's intermediate mass ratio.
If for the long ones, yeah, because it's just so
100.
long.
Okay.
You'll have too many cycles. And so, yeah, that's why I'm letting this happen. And we'll be able to, if we have lots of sources, I didn't get to say this, we'll be able to pull out the population, so you can see little gray curves in there.
Yep.
So these are individual synthetic observations, and made from this kind of 2 lump population, and you can pull that out completely non-parametrically with, a small number of events. We can basically do it now. So like any observation, the data will tell us what's there.
Carl?
I just wanted to revisit like how high we can go in terms of masses. Surely we'll be less susceptible to mistaking glitches for high mass events once we have like 5 detectors online. That's 3 years from now. I mean, you're not going to get a 5 detector coincident glitch. Well, knock on wood.
Carl, do you want to have
Yeah, that's true. That's true.
I'm keeping this.
All right, I want to make one last point that Savik did submit a slide to this section, but we have run out of time to talk about it. But she is chairing the next session, and so she gets to commandeer it and talk about her slide whenever she likes, because she can, and but we didn't get to talk to it. I did make a slide of burning questions, but we don't even have time to put it up, so I'll put it up in the next session. And it can go in the next session as well. So the next session will be really exciting, but enjoy your lunch when we come back, 1:30?
1:30, yeah.
We will return at 1:30. I will see you all then.
Thanks, still